So hello everyone. So today we are going to solve Leetcode problem number 3600, maximize spanning tree stability with upgrades. So in this problem, so we are going to give edges in this format. You can see here, right? And here you can say is U and V. This is a direct undirected edge between nodes U and V, right? And SI is the strength of the edge, right? And there is another variable mass, right? So it's must can have two variables 0 and 1. If much equal to 1, right, then we have to include the edge in the spanning tree and there cannot be any upgrade. And how they are defining the upgrade is, so each upgrade we have to double the strength of an edge, right? And in this problem we can do like maximum k upgrades. And here another definition is given is the stability of a spanning tree is defined as minimum strength score among all the edges included in it. So yeah, so we have to return the maximum possible stability of a valid spanning tree. It's possible, right? So let's understand what is a spanning tree. So spanning tree is nothing but subset of a graph that connect all the vertices together without any cycle and with the minimum possible edges. So that is like classical definition of a spanning tree. So let's take an example, right? Let's take an example for spanning tree. So let's say we have a tree here. Let's say one, two, here. This is a spanning tree. Here. One, two. Okay. So this is a graph we are given, right? So from here, if one can ask us to find a spanning tree, right? So this is one of the spanning tree we can have. So this is kind of like a spanning tree. This is can be another spanning tree. This is can be another spanning tree. Let's say here, here, here. This can be another spanning tree. And let's say take another spanning tree here, right? So this is can be another spanning tree. So from a graph, we can have multiple spanning tree. Only the condition is like it can connect all the uh, nodes, right, with minimum possible edges. So let's say we have n nodes. So in the spanning tree, we are going to have n minus 1 nodes. Uh, that's it. So let's look into some example first. So in the first example, here we have three nodes. So let's say we have node 0, node 1, and then we have node 2, right? So first edges goes from 0 to 1, right? And here, if you see, the strength is 2 and it's masked, right? And second one is goes from 1 to 2. So 1 to 2. So strength is 3, right? So for this one, strength is 3, right? So for this one, so you can say this is the only spanning tree we have, right? So as in the definition says the minimum strength, right? So minimum strength of both the edges is 2. So answer is 2. So answer is 2. Let's look into the second example. So in the second example, you can say is in the second example, you can say is we have again three nodes. So one, let's say we have two here. So first one is like 1 to 0 to 1. So we have here is 4, right? After one is like we have 1 to 2, that is 3. That is 3. After that we have 0 to 2, that is 1, right? That is 1. So this is the spanning tree, and here if you see, so there is no edge here, which is we have to include it, right, for each and every edge. So must is uh, 0. So and k is 2, right? So as we have three nodes. So we are going to have only two edges, right? Max. So there are two possible right, uh, solution here. Either we're going to have this one, either we are going to have two, one, or we can have this one as well, right? Right. So if we're taking this, if we're taking this, then we can do like k upgrades, right? Two upgrades. So this is going to be 8 and this is going to be 6, right? For this one, the stability is going to be 6, right? For this one, it is going to have 2, right? And we are going to have 2, and this is going to be 6. For this one, the answer is going to be 2 because we have to take minimum, right? For this one, if you see, this is your 4, 8, and this is your 2. For this one, the answer is 2. So among all the three, right? So this is the answer. So you can say 6 is the answer, right? Accordingly, right, we can say here as well. So here, if you see, uh, this is the graph, and we have 0, 1, 2. There is 1, 1, 1, right? And here, all the edges are mandatory. So it is creating a cycle. So it's not possible. Not possible, right? So answer is -1. So let's understand how to solve this problem, right? So in this problem, what is given is like we have to create, you can say the spanning tree, right? Spanning tree, spanning tree, right? Which you can say that maximum stability, right? Which you can say maximum stability, stability, right? Maximum stability. And another condition we have is like uh, the must, right? So here, what the spanning tree, when we are creating a spanning tree, there shouldn't be any cycle, right? There shouldn't be any cycle. So here we are already seeing an example where we have a cycle and we are returning -1 from that, right? So cycle, we shouldn't have any cycle. You can say we shouldn't have any cycle. And here in the spanning tree, what we have is number of connected component should be equal to 1, right? So this is one thing we have to follow, right? Another thing is as we have the must, right? So if must equal to 1, so we have to include that edge, right? We have to include the edge. If it is 0, it's optional, right? Optional. And we have a k value, which is like operation, right? Number of operation. Here we can like double the strength of the edge, right? So you can say that. So as the definition says, right, as here definition is, stability of spanning tree is defined as the minimum strength of the scoring, right? And we have to maximize the possible, right? So minimum strength, right? So during constructing the spanning tree, right, what you can say is, as we have to maximize the stability, right? Stability, which is you can say directly proportional to the if we are taking, right, taking maximum strength edges, you can say, right? So if we are taking maximum strength, strength edges, then minimum of this always going to give us that maximum stability of the maximum stability of the tree, right? So another thing we have is around the must, right? Must, right? If one we have to always take. So what we can do here is, so here we are given array, right? Edges array. So what we can do is like initially just take edges, where you can say must is equal to 1, right? Because anyway, we have to take them, right? This is compulsory. After that, if let's say there is more edges to take from the list of our edges, right? So always take in descending order. Always take in descending order, right? And that is the way to solve it, right? When here lots of things, right? Whenever we are uh, uh, like doing the whenever we are building the spanning tree, we have to check this condition as well, right? And yeah, so overall, in high level, what we are saying is first thing is like take edges where must equal to 1, right? After that, you can say is like short edges where must equal to 0. Take edges till, you can say till number of edges equal to n minus 1. Sorry, it's not coming, but yeah. So that's the how we are going to solve this problem. So let's look into the code. Yeah, so this is kind of like Java implementation of the solution. I'm going to divide the solution into two parts. The first part is like how we are going to detect uh, whether we have a cycle or not, and how we are going to like detect how many connected components we have. So basically everything we can do using union find. So this is the code for union find to find everything. So this is kind of like very basic union find code. So here we have a parents, right? And we have number of nodes here. And this is like we have number of components here. So whenever we are doing union, right, we basically assign, whenever we doing union, so we basically assign the parent of the source to the parent of, you can say, uh, parent of the destination. And after that, if let's say parent is not equal, so we are basically merging two nodes, right? So we are going to decrement the number of components. So if you see here, so number of component is n in the initially. After that, whenever we are merging the nodes, we are like uh, decrementing the number of components. And here itself, we can detect whether we have created a cycle or not by just checking this parents of source and parents of destination. If both are same, means uh, it is a cycle. And in number of distinction, we are already like calculating here. Right? It's pre-calculated against the components variable. This is the actual implementation of the solution. So here we have defined a union find data structure here, right? After that, we are iterating through all the edges, right? And wherever the mask is one, right, we are calculating the stability as the minimum of the all the edges, right? Then after that, completing this loop, we are just checking whether number of edge taken is n minus equal to n minus 1 or not. So if it is n minus 1, means we are good with all the edges, right? But there is also a catch, right? So after taking n minus 1 edges, right, whether it's a single connected component, like it's a kind of like disjoint sets, right? So if it is a disjoint set, so we are going to return minus 1. After that, in the first loop, whenever this master is not equal to 1, so we are adding all those edges to a list. So we are sorting those elements here based on their stability value. After that, like we are again calculating the stability, right? If number of operation is left, right, we are taking twice the value of the strength. If it is not, so we are taking only the strength, right? And after completing this loop, again, like, we are calculating the number of uh, like number of components and checking again here. It should be one, else like we have this join set, so returning -1. After that, like, we are returning the stability. Let's submit this code. Yeah. So that's all for today, guys. See you in the next video.